Hello everyone, my name is SN Patil. In this video lecture, we will discuss properties and theorems of Fourier transform. First, let us see linearity property of Fourier transform. If Fourier transform of f of x and g of x is capital F of lambda and g of lambda, then Fourier of the linear equation, that is C1 f of x plus C2 g of x. Here C1 and C2 constant, okay, is equal to C1 f of lambda and plus C2 g of lambda. Okay, so first we define the formula and then apply the definition of Fourier transform. Let Fourier transform of f of x is denoted by capital F of lambda and defined by the formula minus infinity to plus infinity f of x e to the power minus I time lambda x with respect to x integration. Say equation number 1. In some book, some author here take the 1 upon under root 2 pi. You can take 1 upon under root 2 pi, otherwise skip it. If we take 1 upon under root 2 pi, then in it inverse you have to take the 1 upon under root 2 pi, otherwise neglect it. Okay, so here I am taking here direct formula minus infinity to plus infinity f of x e raised to minus I lambda x dx. Okay, now similarly the Fourier of the g of x function is capital G of lambda, okay, and it is defined similarly minus infinity to plus infinity g of x e to the power minus I time lambda x with respect to x integration. Say equation number 2. Okay, if Fourier operate on the function, then integration of that function. Similarly, the Fourier of this linear function, Fourier of the linear function c1 f of x plus c2 g of x is equal to, we apply the formula minus infinity to plus infinity inside the integration, the given linear function c1 f of x plus c2 g of x e to the power minus I lambda x with respect to x integration. Now first of all we apply the linearity property of integration, that is integration of first term plus integration of second term. At the same time the exponential function is multiplied to the first and second term. Okay, now here when we apply integration of the first term where c1 is constant, we write outside the integration minus infinity to plus infinity f of x, and the exponential term is multiplied e to the power minus I lambda x dx, plus in for second term where c2 is constant minus infinity to plus infinity g of x e to the power minus I lambda x with respect to x integration. Now from 1 and 2, the first integral we denote as a capital F of lambda and the second integral we denote as a capital G of lambda, that is c1 capital F of lambda and plus c2 capital G of lambda. That is the Fourier of the c1 into f of x plus c2 into g of x is equal to c1 plus capital F of lambda plus c2 into capital G of lambda, where f and g both are the Fourier of f and f of x and g of x. So this is the linearity property. Now let us see the second property, change of scale property. Okay, see, this is the Fourier transform of f of x is capital F of lambda. Okay, then the Fourier of f of x. Okay, so this is a scaling property in a domain. It is rapidly increase the function. Okay, that is f of x is equal to 1 upon a in output side, 1 upon a f of lambda upon a. Okay, so first of all we write the formula for Fourier transform and we apply the formula for the given problem, given property, that is the Fourier of the given function f of x is denoted by capital F of lambda and defined by the formula minus infinity to plus infinity f of x e to the power minus I lambda x with respect to x integration, say equation number 1. Okay, that is the Fourier of f of x. Now we similarly we find out the Fourier of f of ax. Okay, that is the Fourier of f of ax is equal to integration minus infinity to plus infinity. When f of x is here, then f of x. Instead of f of x, if you put ax, f of ax, then we write here f of ax. Okay, e to the power minus I time lambda x with respect to x integration. Say equation number 2. Okay, now here f of x, this is the variable simply x. So similarly here we write the simple variable. So we make the substitution. Instead of ax we substitute the t, yeah, u. Okay, put ax is equal to t, that is we transfer x to the t. This is the integration for x. Now we transfer x to the t. Similarly the differential term is also change. We differential, okay, where x is function as a t, that is dx by dt is equal to here 1. Then dx is equal to a, dx is equal to dt is multiplied here, and the a is divided, that is 1 upon a dt. Now these are the limit for the x. Now new limit we obtain for t. When we put x is equal to minus infinity, then t is minus infinity. When we substitute x is equal to infinity, then t is infinity. There is no change in limit. Okay, is equal to, substitute in equation 2. So we got the Fourier of f of ax is equal to, as it is limit minus infinity to plus infinity f of t e to the power minus I time lambda. The x is changed. X, what is the value of the x? X is, the a is divided, that is t upon a. So here t upon a, and the dt, the value of the dx is 1 upon a dt. Okay, so here 1 upon a is constant term. 1 upon a minus infinity to plus infinity f of t e to the power minus here we write lambda upon a into t dt. Now see the formula number 1. In formula number 1, in integration f of x e to the power minus I lambda x dx, the coefficient of minus ix is lambda, then write here f of lambda. Okay, the coefficient of minus ix and the integration with respect to x. So identify the coefficient of minus x in exponential power, that is the lambda, write lambda here. Now here the integration with respect to t, the coefficient of minus time it is lambda upon a, then we write capital F of lambda upon a. Okay, so this is the required change of scale property. The Fourier of f of ax is equal to 1 upon a f of capital F of lambda upon a. Now see, the second property is shifting property. If the Fourier transform of f of x is f of lambda, yeah, f of lambda is Fourier transform of f of x, then the Fourier of f of x minus a, that is the shifting in domain, okay, is equal to f of is equal to e to the power minus I lambda f of lambda. First we write the formula as usual. The Fourier transform of f of x is denoted by capital F of lambda and defined by the formula minus infinity to plus infinity f of x e to the power minus I lambda x dx with respect to x integration, say equation number 1. Now apply the definition for the given problem, that is the Fourier of shifting x minus a, okay, that is the right hand side shifting, is equal to, apply the definition, minus infinity to plus infinity. If f of x is here, then we write f of x. If x minus a, f of x minus a, we write x minus a, f of x minus a e to the power minus I lambda x dx. Okay, same kind of the property, previous property we discuss, here ax is there and we make the substitution ax equal to t. Similarly, we make the substitution x minus a is equal to t. So put x minus a is equal to t, then see x we transfer to the t, then dx also transfer, then differentiate, the derivative of minus a is 0. Here t we differentiate actually t, that is the 1, and dt is multiplied, that is dx is dt. Now limit, when we put x equal to minus infinity, then t is minus infinity. When we substitute x is equal to plus infinity, t is plus infinity, there is a no change. Okay. Also here we get the value of the, let us also find out the value of x. The x is t plus a. Now suppose this is equation number 2. Substitute in equation number 2, then Fourier of f of x minus a is equal to minus infinity to plus infinity. Limit is as it is. Here f of t e to the power minus I lambda. The value of the x is t plus a in bracket, and the value of the dx is dt. Now here we simplify, minus I lambda is multiplied to the first term t and second term a. Now it can be written as minus infinity to plus infinity f of t e to the power minus I lambda t, okay, and minus I lambda a dt. Now here the exponential function as like e to the power a plus b. Okay, we write e to the power a, e to the power b. That is, we write e to the power minus lambda t minus I lambda a is equal to e to the power minus I lambda a, e to the power minus I lambda, sorry, I lambda t, I lambda a, where e to the power minus I lambda is constant because this is integration with respect to t. Here I am writing constant term outside the integral, inside the only function of t, that is f of t e to the power minus I lambda t dt. Okay. Now from equation number 1, here this is the definite integral. The variable is not important. Instead of x, if we substitute the t here, then f of t e raised to minus I lambda t dt, that is the its Fourier is f of lambda. So we write the term as a, the value of the integral as a capital F of lambda. Indefinite integration is indefinite integration, the variable is not important. Okay, the capital F of x minus a is equal to e to the power minus I lambda a into f of lambda. This is the shifting property. Same kind of the property, translation property, that is the shifting in a codomain set. Okay, that is in output set. If f of lambda is a Fourier transform of f of x, then Fourier of exponential into f of x is capital F of lambda minus a. Okay, as usual we write first formula, and then simplify for the given problem. Let capital F means Fourier of f of x is denoted by the capital F of lambda is equal to, and it is defined by the formula minus infinity to plus infinity f of x e to the power minus I lambda x with respect to x integration, say equation number 1. Okay, now here we find the Fourier of exponential function e to the power minus, sorry, plus ax f of x is equal to minus infinity to plus infinity. If f of x is here, then we write f of x. Okay, if here e to the power I ax into f of x, we write e to the power I ax f of x into e to the power minus I lambda x dx. Okay, now we simplify the exponential function. Base is same, addition of power. Okay, that is, it can be written as minus infinity to plus infinity f of x e to the power. Now here we take minus I is common, and x is common, then what is remaining term here? Lambda is remaining minus a is remaining, x dx. Now see what is see the simplification. What is the term in power? I a x minus I time lambda x. We take minus I is common. What is remaining? Uh, Here when we take minus I is common, then plus lambda is remaining, and here the plus and here minus sign is common, that is minus a is remaining in, and we take x is common in this way. Okay, now from equation 1, Fourier of e raised to I a x f of x, from equation number 1, the coefficient of minus ix is lambda, then we write f of lambda. Same concept we apply here. The coefficient of minus ix is lambda minus a, then we write f of lambda minus a. So this is the required translation property here. Okay, now next last theorem, that is modulation theorem. If f of lambda is a Fourier transform of f of x, then Fourier of f of x into circular, okay, that is the cosine, is equal to 1 upon 2 f of lambda plus a plus f of lambda minus a. So first of all, we write the formula. uh, Fourier of f of x is equal to capital F of lambda, and defined by the formula minus infinity to plus infinity f of x e to the power minus I lambda x with respect to x integration. Okay, now we find the Fourier of f of x into cos x. Apply the formula, that is Fourier of f of x into cos of ax is equal to, apply the definition, minus infinity to plus infinity. If f of x, then we write f of x. Okay, if here f of x into cos, then write f of x into cos, f of x into cos. Okay, f of x into cos into e to the power minus I lambda x with respect to x integration. Okay, so here we simplified this cosine term in terms of exponential function. We know that the cos theta is 1 upon 2 e raised to I theta plus e raised to minus I theta. Okay, and theta is here ax. Now it can be written as minus infinity to plus infinity f of x, the value of the cosine function we write in terms of exponential function, that is 1 by 2 e raised to I time ax plus e raised to minus I time ax into e raised to minus I lambda x dx. Okay, is equal to, here 1 by 2 is constant. Okay, now first I am applying the linearity property of integration, the f of x and this exponential function multiplied to the first term and plus multiplied to the second function. Now minus infinity to plus infinity f of x e to the power I ax e to the power minus I lambda x with respect to x integration. Now plus multiply to the second term f of x and this exponential function. Okay, that is minus infinity to plus infinity f of x e to the power minus I ax into e to the power minus I lambda x dx. Okay, now is equal to 1 by 2 in bracket minus infinity to plus infinity f of x e to the power. Now see, we discussed the power term. In first term, I ax plus base is same, addition of the power, here minus I time lambda x. So we take minus I is common and here x is common. Then what is remaining term? Lambda minus a is remaining. Now in second term, minus I a x minus I lambda x. So we take minus I is common and x is common. When we take minus I is common, remaining here a, and here plus lambda. Here the first term we write minus I in bracket lambda minus a into x dx. Now plus in second term minus infinity plus infinity e to the f of x e to the power minus lambda plus a, lambda plus a. Okay, with respect to x integration. Now from equation 1, the coefficient, if the coefficient of in power, exponential power, the coefficient of minus ix is lambda, then write the f of lambda. Same concept we apply here, that is 1 upon 2 capital F, the coefficient of minus ix is lambda minus a, plus capital F, the coefficient, sorry, here x is remaining, the coefficient of minus ix is lambda plus a. Okay, and we know addition is commutative, so it can be written as the Fourier of f of x cos of ax is equal to 1 by 2. Addition is commutative. First we write capital F lambda plus a plus f of lambda minus a. Okay. Thank you.